Hello everyone, today we're going to be talking about the RC high pass filter. You can see it right here, and it consists of one resistor and one capacitor put in this order. Now what I'm going to try to do is make you understand what happens here mathematically and make you get some intuition about it, and then draw some Bode plots so you have the full picture. So here we have two components, R and C, and we can write them into impedances, and the impedance of the resistor is just R, and using the Laplace transform, the impedance of a capacitor is 1 divided by SC. And if we treat them like impedances, we can use the voltage divider formula, which would be like this. VO, we just call it VO, equals ZR divided by ZR plus ZC multiplied by the input voltage. And now we substitute for ZR, which is just R, divided by R plus 1 divided by SC multiplied by VI. So now we just want to make one clean fraction. R, we can rewrite it as R divided by 1. So it's easier for us to do a one clean fraction. And here, this we multiplied by SC, this by 1. So we have R divided by 1, SCR plus 1 divided by SC, VI. Now here we multiply the top by the bottom and the middle by the middle. And we have SCR in the numerator divided by SCR plus 1 VI. Now, if you remember, we started from VO, so this is equal to VO, okay? And now we want to arrive from one side to have this, which is the gain. And it's logical to think that this is the gain because, for example, if we have in the output 4 volts and in the input 2 volts, then we have a gain of 2. We have more in the output than in the input, and we created some type of gain. Now, here we cannot have a gain bigger than 1 because we have just a resistor and a capacitor, and we cannot create energy out of nowhere. So this I said just to get some intuition, but to arrive to VO divided by VI, we just divide by VI, and we have that VO divided by VI equals SCR divided by 1 plus SCR. This seemed just more good looking. And this we also call our transfer function, which we write like this, H of S. Okay. And to understand better how this filter works, I think it's useful to see also the frequency response, which you get if you substitute S with J omega, where J is an imaginary unit and omega is the angular frequency. Now that way we would have H of J omega equals to J omega instead of S, okay, CR, divided by 1 plus J omega CR. And why is this useful? Because here we can substitute for omega for low frequency, and we will write it as omega tends to 0, or omega tends to infinity for high frequencies. And since this is a high pass filter, we want our filter to let high frequencies in and to block low frequency, okay? So let's try for both cases. If we do the limit of omega tends to 0, we have 0 divided by 1 plus 0, which is 0 divided by 1, and here we have 0. So what this means in translated in human words is that if you put a signal that has low frequency, our frequency response says that it will block them all because the result is 0. So until now, our result is verified as we want. And let's try for high frequencies, infinity. And here we can immediately see that if we substitute, we have infinity divided by infinity. So we cannot do that. So let's just take this term in front of the parentheses, okay? And then we have 1 divided by J omega CR plus 1. So this cancels out with this, and we are left with the limit we rewrite in the same way, 1 divided by 1 divided by J omega CR plus 1. This term right here tends to 0, so we just have 1 divided by 1, which is 1. This means that at high frequency, the whole signal passes. Now, an important part of filters is also knowing how to design them, and a very simple way to design them, which is not used frequently, but it's a simple way, is to have the frequency at the x-axis, the gain at the y-axis, which would be just, this is the same as saying V out divided by V in, okay? And we draw something like this. So here it means that at low frequencies the signal doesn't pass, and at high frequency the signal passes. But the problem here is that if you want to see at the same graph, at the same plot, if you want to see 100 hertz and 1 million hertz, you cannot do that, because here you would usually have something like 100, 200, 300. So 1 million is very far away. And that's where Bode plots come in, because you plot things here on a logarithmic scale, and here at the same graph you can have very low and very high frequencies. So here at the x-axis we have omega, which will be the number that we put here, and at the y-axis we'll have the gain but converted in dB. So we'll write log 10 gain, okay, and this right here converts a scalar gain into a gain in dB, okay. And what's interesting about this graph, and I will write it a little bit more long here, is that in our case this filter will be all below the x-axis, and I will explain to you why. Now, before I said that our maximum gain in this filter can be 1, okay. So if we plot our maximum gain of 1, okay, we will get 0 here. And for a high pass filter, which means high frequencies, we will have 0 here. And for anything below that gain, let's say 0.9, we'll have something negative. Okay, now to do the Bode plot successfully, we first need to find the zeros and the poles, and then we'll draw the Bode plot. Now, how to find them is, to find the zeros, you put the numerator equal to 0. So here we have S here equals to 0, S equals 0. Now, this is the 0 that we have. And to find the poles, you just put the denominator equal to 0, okay? And here we have SCR equals -1, S equals -1 divided by RC. So this is our pole, so we'll just write it as P1, and this is our 0, so we'll just write it as Z1, okay? Now, what these zeros and poles do is that the magnitude plot, this is the magnitude plot, Bode plot, okay? And when there's a 0, it introduced an increase of 20 dB per decade, so we'll have something like this, a slope, and when there is a pole, we will have a decrease of 20 dB per decade, so we'll have something like this, okay? Now, these increases and decreases happen at something that's called a break frequency, and to find the break frequency, we'll do the following. So first, we design zeros and poles on S-plane, okay? So here we got that S is 0, and here we got that S is -1 divided by RC. So we'll plot it, and S is the Laplace transform variable, which is equal to sigma plus j omega. And the x-axis is sigma, and this is j omega, okay? And now here we have first S equals to 0, and this was our 0, okay? And we'll just write it as a circle. And our pole was S equals -1 divided by RC. And this was our pole. And you can see that this here only has a real part, -1 divided by RC, but it doesn't have something like +5J or something like that. So since it doesn't have that part, it is purely on the x-axis and in a negative part specifically. So we'll just draw it right here, and we'll call it -1 divided by RC. This is our pole, and I denote it with X. And now to find break frequencies on Bode plot, you need to calculate the distance from 0 or pole to origin. Now, you know that the distance in numbers, and let's say in complex numbers, is the real part of the first one minus the real part of the second number squared, plus the imaginary part of the first one minus the imaginary part of the second one squared. So this is the formula for finding the distance. So now we need to find two break frequencies. So first we need to find the distance from this point right here to this point right here, and then the distance from this to this, which is the same distance, so we already know it's 0. But let's start with the pole. So here we have 2 points, -1 divided by RC plus 0J, because there's no imaginary part, and the second point is 0 plus 0J, which is the origin. So we have the real part of the first one, which is 1 divided by RC, minus 0 squared, plus 0 minus 0 squared. So this is equal to -1 divided by RC squared, which is equal to 1 divided by r squared c squared, which is equal to 1 divided by rc, which is equal to the break frequency of the pole. We'll just write p here. And since the second distance is basically from our 0 to the origin, which is just 0 minus 0 plus 0 minus 0. So this is just 0, which is the break frequency of the 0. Now what this means is that at the frequency 0, there will be an increase of 20 dB per decade, since we have a 0 here. And at the frequency 1 divided by RC, which we'll say that it's right here, it will have a decrease of 20 dB per decade. And when you have plus 20 increase, minus 20 decrease, you will have a 0. So you will just have a flat line right here that will continue until the end. And we just draw it like this with straight lines because it's easier to design it that way at the beginning. But at the end, you should have a smooth graph. So you will just draw a smooth line just below it. So the green part is the actual Bode plot. And now we're going to draw the phase Bode plot, which will have the same x-axis, and as the y-axis it will have the argument of the frequency response, or some people just write it as this. I think this is much more common notation. And we already know that we have a 0 at omega equals 0, and we have a pole at omega equals 1 divided by RC. And a 0 creates an increase of p divided by 2. And a pole creates a decrease of p divided by 2. So here at omega equals 0, we have an increase of p divided by 2. We'll denote it like this. And we go until a certain part. We continue going until we reach our pole, which will do a decrease of p divided by 2. And it will just continue to go like this. Now, same as before, we just draw straight lines right now. But after, you draw a smooth curve like this. And this is your actual phase Bode plot. Now, thank you all for watching. I hope you got the intuition and you now understand fully what this filter does and how to draw the plots. And in the next video, I'm going to be talking about the low pass filter. So if you like this video, make sure to subscribe so you also see the other video.